During this devastating pandemic, we have seen many patients suffering from heart disease associated with this coronavirus.
Thanks to you, we've been able to use our unique technology to sequence hundreds of coronavirus patients.
We are doing that by developing a novel method of using antibodies to detect virus-infected cells in patients and be ready for use in the very near future.
This is all because you stepped up to the challenge.
We look for viral proteins that are being presented by human cells to the immune system. And so this potentially could lead to new options for vaccination.
With your support, we're developing drug candidates against COVID-19 and may help us in the current pandemic and future pandemics as well.
And thanks to your support, we've been able to develop a cyclic strategy that's now used in schools and companies to balance health and the economy.
We are utilizing the single molecule systems in our lab to develop a new technology for COVID diagnostics.
We're using advanced high-field magnetic resonance spectroscopy techniques to elucidate the structure of the coronavirus genome, and with that information develop drugs to tackle the disease.
With your generous support, now we're seeking industrial partners that will be able to take this molecule further into the clinic.
Thanks to your support, we could focus all our efforts on how to most efficiently use testing to fight COVID, how to decide how to use the days of quarantine in the most efficient way, and how to analyze and visualize the data of the epidemic in Israel and around the world.
We have found a way to inhibit coronavirus infection in tissue culture utilizing existing approved drugs.
Because you stepped up to the challenge.
We examined the immune buffer exit strategy by using our mathematical model for it, to use the help of people who recovered from the coronavirus in helping people who are at high risk of getting infected.
Because you stepped up to the challenge.
So now we are able to isolate antibodies from COVID patients and study them in the lab and better understand how they engage in efficient immune response against the virus.
These antibodies help us to define the right area in the virus for vaccine design.
We can do it because you stepped up to the challenge.
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 So it's your kind and warm support that makes our research comes true.
It is indeed heartwarming that all these scientists were able to put aside their own research goals, and that our friends have been equally altruistic and have given us a helping hand at a time of urgent need. I'm thrilled to be introducing this session about Weizmann's coronavirus research. We will have a live Q&A session at the very end of the event, after the prize ceremony. So please hold your questions until the end of this session, and we will open the chat box function shortly before the Q&A. We will try to get through as many as we can. Thank you. So let's begin. In Hebrew, we have an expression, כשהאסימון נופל, for those moments when something big has happened and we have a mental delay in getting it. Just like when the penny drops, I guess. When the coronavirus pandemic hit, the world wasn't prepared. And it took some longer than others to come to terms with this new reality. In February, I was in the US on a trip to meet some of our dedicated Weizmann friends. And there were no masks in sight, and I too was going along business as usual. Meanwhile, back on campus, in Rehovot, the penny has already dropped for many of our scientists, especially the life scientists. By the time my plane touched down in Tel Aviv, Dr. Nir London, whom you'll hear from shortly, has already started screening drug compounds in his organic chemistry lab. What he was looking for was molecules that might immobilize or inhibit the coronavirus. Just about the time I was getting over my jet lag in early March, Nir has already sent out a worldwide call to chemists to crowdsource ideas for the most promising molecule design. By mid-March, more than 60 projects had sprung up across campus focused on understanding the virus and finding solutions for testing, contact tracing, and possible drugs and vaccines. We in management immediately put together a funding pipeline for a coronavirus response fund, and we turned to our supporters. I have to say that the penny dropped equally fast among our supporters as it did among our scientists. More than 170 donors collectively gave many, many pennies, $13 million to be exact so far, and the gifts continue to come in. We are very grateful for this outpouring of support. From the management perspective, in establishing the Coronavirus Response Fund at Weizmann, we also already begun thinking about the day after. What happens after we are all vaccinated and the pandemic is behind us? So as part of this fundraising effort, we aim to establish an Institute for Infectious Disease Research. This new entity will leverage the insights from the coronavirus research and fund ongoing infectious disease research so that we are always one step ahead. When talking about the coronavirus, it's natural to also think about the psychological aspect. Our scientific presentations will be followed by a conversation with Professor Dan Ariely, who will take us with him on an intellectual journey around human behavior and psychology in times of crisis. And so it's an apt moment to hear from him. Nir London certainly didn't waste any time moving ahead, so I will not waste any more time, and let's get right to him. Nir, please.
In the middle of February 2020, it was already clear that a mysterious flu-like epidemic that erupted in China only a few weeks earlier is going to spread globally. That's why when I got an email from Professor Frank van Delft, a longtime collaborator of mine from Oxford University, I didn't hesitate. We have the main protease for the new coronavirus. Should I send it to you, he wrote? Of course, I wrote back. Send it ASAP. When the virus infects our cells, it uses the cellular machinery to translate its genome into one long protein chain, which is inactive. The main protease, this Pac-Man-like protein, cleverly cleaves itself out and proceeds to free the other viral proteins, activating them and allows them to hijack the various cellular systems. This is an essential activity for the virus. Hence, blocking the protease will kill the virus and would not allow it to replicate in our cells. This will not be a vaccine, but a cure, a treatment for patients who have already contracted the disease. Our goal was simple: to develop a cheap and safe antiviral against SARS-CoV-2, faster than the traditional drug discovery pipeline. In collaboration with Diamond Light Source and Oxford University, we screened thousands of tiny fragments against this protein. The reason Frank approached me in the first place is that the protease is particularly susceptible to the technology that we have developed in our lab. We use mass spectrometry to identify compounds that are able to stick to the protease irreversibly. This combined effort resulted in tens of structures, atomic resolution snapshots, defining a blueprint of how this protein can be inhibited. Each one of these fragments in itself is too weak to inhibit the protein, but if merged in exactly the correct way, they could result in a potent inhibitor. The data was promising, but the search space was too big to explore on our own. We decided to crowdsource the problem. Postera, a San Francisco-based company led by Alpha Lee, helped us launch the COVID moonshot and built for us, almost overnight, a web platform that allows chemists from around the world to explore our data and suggest ideas for next-generation inhibitors. We turned to social media to recruit the wisdom of the crowd. This was late March, at the height of the first wave. Everyone was in lockdown. Many were frustrated that they cannot contribute to the fight against the pandemic. The response was overwhelming. Hundreds of people submitted thousands of designs. From PhD students to veteran pharma employees, we now had to sift through these suggestions, most of them completely unique, to find the diamonds in the rough. We enlist machine learning, computational chemists, and medicinal chemist volunteers to prioritize them. Chemical synthesis companies, and in particular Inamine, are making these compounds for us, almost at cost. Each week, we get a shipment from Inamine with new compounds and test them for protease inhibition. In parallel, Oxford are attempting to determine their structures. We report the data to the world in real time. This is the place to mention that one of the unique aspects of this initiative, which also allows us to operate so quickly, is that we operate completely in the open. There's no intellectual property, no material transfer agreements, no waiting for publication in scientific journals. Data is released to the public in real time. So far, we've made and tested over 1,300 compounds and identified several promising inhibitor series on which we're currently focused. This is an example of perhaps our best candidate series. A researcher from the UK submitted a design that was based on a merge of two fragments. It showed weak activity, only 23 micromolar. This number indicates the concentration of the molecule that is required to inhibit 50% of the protease activity. It wasn't very good, but it was a good starting point. We started to tweak and adjust various parts of the molecule and were able to improve it. Second-generation designs improved its activity by 10 to 30-fold. And we pushed on, and recently, a fourth-generation design showed very potent inhibition, representing over 150-fold improvement from the original merge. We teamed up with Folding at Home, a crowd computing platform that uses the spare cycles of computers across the world and is now 10 times stronger than the world's fastest supercomputer. Led by John Condera at Memorial Sloan Kettering, we used this vast computational power to simulate the binding of candidate designs to our target and further optimize our best inhibitors. This is just another example for the collaborative nature of this initiative that truly spans the globe. Over the past 2 months, collaborators at the Israel Institute for Biological Research, University of Chicago, Oxford University, and more have been testing our best candidates against the live SARS-CoV-2 virus in cells, no longer against a single protein in a test tube. And I'm happy to announce that they work and are within reach of preclinical potency. We're scaling up their production, crossing the T's and dotting the I's to enable their testing in animals. To become a drug, they need to pass additional hurdles other than killing the virus. They need to pass the liver, they need to get into the lungs, they need to be safe and not show any side effects. This is the reason developing a drug can take years and cost between $1 and $2 billion. However, the fact that within 8 months, in the midst of a pandemic, we took a concept from a rant on social media to a potent compound that is starting to look like a bona fide preclinical candidate gives me hope. All it took was the combined resolve of more than 130 scientists across many nations, united in the vision that open science can combat this pandemic. It may still take years to become a drug, but if we work together, we can make it, and we'll be ready for this and future pandemics. Thank you.
Thank you, Nir. That was fascinating. While Nir is on one side of the scientific equation, figuring out how to make the best drug, other scientists are hard at work figuring out just what the coronavirus is and how it behaves. So let's take a step back to understand about how viruses work. Dr. Noam Stern-Ginossar's research in the Department of Molecular Genetics involves discovering how viruses invade healthy cells and take over the cell's systems to survive and reproduce. Noam, we want to know how and what you found. Noam, please.
Good evening and good morning. My name is Noam. I come from the Department of Molecular Genetics, and I'll tell you a little bit about the work my lab has been doing to understand the coronavirus. So what is a virus? The term in Latin means poison, and it was coined by Louis Pasteur when he was trying to understand what caused the rabies disease. He was able to isolate a material that can transfer the disease, but when he looked at this material under the microscope, he could not see anything. And this made him realize what causing the disease is not bacteria, but a virus, a poison. Today, we know that viruses are actually simple genetic materials that is packed in a protein shell. By itself, the virus cannot really do anything. It doesn't move, it doesn't replicate, and only when it infects a cell and injects its genetic materials, it forces the cells to generate many new viruses. Viruses are found all around us. They actually infect all live organisms, It can even infect bacteria. Viruses come in many different shapes and flavors and sizes. And actually, most of the viruses around us can't really infect us. So they infect really specific cell types. Generally, we divide viruses based on two categories. The first one is what is the genetic materials they have, whether it's RNA, like the coronavirus, or DNA, like herpes viruses, that infects the majority of the human population. In addition, some of the viruses have envelopes around them, and then we call them enveloped viruses, where there are naked viruses, like the poliovirus. The first thing that happens when a virus meets a cell is we have a direct interaction between the surface of the virus and a receptor on the infected cells. If this recognition occurs, the virus will inject its genetic material, and this material will get into the cell and will be recognized by a cellular machinery that is called the ribosome, which will convert this genetic material into proteins, which are these colorful dots that you are seeing. And these proteins will be the actual identity that will force the cells to make new viruses. So what we wanted to know in my lab is which proteins is the coronavirus coding for. And what we've done, we took cells in the lab and we infected them with the coronavirus, and then used a sophisticated method that allows us to look at exactly what the ribosomes are translating in infected cells. And this allows us to accurately quantify how much of each of the coronavirus protein is being made. So for example, in this graph, you can see that in infection, there is much more being made from the yellow protein, which is the nucleocapsid, compared to the RNA polymerase, which is the green protein. And this is important because first it teaches something about how the virus works in infected cells, but also it can really guide diagnostic efforts, because when we want to do diagnostic, we want to target it to abundant viral proteins. In addition, when we've done this experiment, we actually were surprised to identify 20 new viral proteins that are encoded by the coronavirus. Some of these proteins are really highly conserved, suggesting they play an important functional role in the pathogenesis of the coronavirus. So overall, our finding really build a framework for understanding the pathogenesis of the corona and for revealing new therapeutic targets. We still have a lot of open questions, and we are looking forward to see where the research will lead us. Thank you.
Thank you, Noam. I know it's hard for most of us to imagine another threat after corona, but that's okay. We don't all have to imagine. Weizmann scientists do that for us. And the threat that Dr. Roi Avraham is very worried about is a pathogenic bacteria against which we may be totally powerless if current antibiotics fail. Dr. Avraham is a member of the Department of Biological Regulation. To help make sure we are always one step ahead, Roee is conducting research that he will tell us about now. Roee, please.
The world is slowly moving towards a global health crisis, the global spread of antibiotic-resistant bacteria. Antibiotics, which were introduced about a century ago, are the most important drug in modern medicine. It has increased life expectancy worldwide more than any other drug. However, resistance has not crept up on us. Already in 1945, Sir Alexander Fleming, upon receiving his Nobel Prize for the discovery of penicillin, mentioned that the misuse of antibiotics will render the bacteria resistant to its effects. And of course, we have not listened. In the past decades, we have witnessed resistance emerge against any known kind of bacteria. And resistance is so prevalent today that we find MDR and XDR bacterial strains. These are multi-drug resistant and totally drug resistant bacteria, or superbugs as they are called. They have no effective treatment against them. It is predicted today that 700,000 people die annually from resistant infections. And this number is predicted to skyrocket in 30 years to 10 million a year. This is more than cancer. Now, while new antibiotics are really in a need, these are not forthcoming. The reason is that introducing a new drug into the clinic is very expensive and takes a lot of effort. And these are rendered ineffective very quickly by the emergence of resistance. Now, what is resistance actually? I will demonstrate to you in a short film where we will see bacteria marked in green grown in rich agar, which might resemble what happens in our body during infection. And you can see that the bacteria grows, and probably we will feel sick at that point, go to the doctor, receive an antibiotic regimen, and start taking that regimen. The bacteria will quickly die from this antibiotic treatment, but what you can see surprisingly is that some of the bacteria resist this treatment, and they will stay throughout the antibiotic regimen. Once we are finished with the antibiotics, this bacteria will soon take over. As an alternative, what we want to propose is to use our body immune defenses. What was once considered a rare event, today it is clear that the immune system is facing all the time microbes that are inside our body or that we pick up from the environment, and they keep them in check, removing this threat very quickly after the exposure. However, sometimes immunity fails. Now, because we are so reliant on antibiotics, we don't know the answer to a very simple question, and that is, why do some people get sick and some don't? The answer to this question we propose is probably the next generation of infection therapeutics. Let me explain. Upon entering our body, the bacteria will not grow happily as you saw in the movie I showed you before. It will encounter a poor nutrient environment. It needs to adapt to this environment in order to get its meals. If we understand this adaptation process, we can expose a crucial vulnerability of the bacteria. What's more, within our tissues, the bacteria needs to defend itself against host attack. If we understand these delicate host-pathogen interactions, we can disarm the bacteria and leave it non-infectious. In order to realize these important opportunities, crucial points of infection, we need to understand what is going on at early stage of infection. This is not an easy task. During this period, bacterial numbers are very small, which renders them a blind spot for current research capabilities. In order to understand what happens during the early stages of infection, that means from the initial inoculation with very few bacteria until the appearance of symptoms, we developed in our lab very sensitive tools that allows us to probe the interactions of single host cells and a single bacteria. This breadth of information will allow us now, and already allows us, to propose treatments that will change the course of infection, either by boosting immunity or by targeting the pathogenicity of the bacteria. We believe that this approach holds great promise because there are no known mechanisms of the bacteria that can raise resistance against this process. Thank you.
Thank you, Nir, Noam, and Roee. I don't know about you, but I can speak for myself at least by saying I'm now a bit shaken by the scientific reality of the coronavirus and the threat, the next pandemic around the bend. So the timing is perfect for a little bit of therapy. Professor Dan Ariely is just the man to help us out and help us to understand ourselves a little bit better. Dan is a professor of behavioral economics at Duke University. He's currently a visiting faculty member at the Weizmann Institute. You may have heard his TED Talks, which have been viewed more than 15 million times, or read his best-selling book, Predictably Irrational: The Hidden Forces That Shape Our Decisions, and his other popular books. Dan, thank you for joining us from North Carolina.
Lovely to be here from a distance. I'm with my third cup of coffee. Looking forward to our discussion.
All right, it's evening here. Listen, Dan, I have to admit, this whole new world of coronavirus is really frightening, and I have to admit it's not an easy situation to get accustomed to. What can you say to help?
Okay, so I'm very happy that you started with fear, but let me ask you, and let's see what you're willing to share, is what exactly are you afraid of? What's the range of things that you're afraid and worried about?
I'm afraid of getting sick. I'm afraid of someone in my family maybe getting sick. One of my daughters has asthma. Not to mention my elderly parents. I'm afraid that my research would be compromised. I'm afraid of losing my job. Actually, I can't lose my job. I'm a tenured professor at the Weizmann Institute.
So first of all, let me tell you, you're not alone. So maybe that helps a little bit. But think about what fear and stress are all about. And maybe one of the most important experiments was done on dogs many years ago. And think about the following setup. Imagine there's a room, and there's a dog in that room, and from time to time there's a light. And a couple of seconds later, the dog gets electrical shock. Light, electrical shock, light, electrical shock. The light is in a random time, and then there's electrical shock follows always 2 seconds later. That's dog number 1. Dog number 2 gets the same shocks as dog number 1, but he doesn't get the warning. There's no light that comes in. Now think about those two dogs. What's the difference between them? They experience the same pain, the same electrical shocks, but one of them, the shocks are predictable, and for the other one, it doesn't. What's the difference? To look at what the difference is, they took those dogs and they put them in a new situation, a new room, with a low fence in the middle. And from time to time, there's a bell. And if the dog stays on their part, on their side of that room, they get electrical shock. But if they jump over the partition, they avoid the electrical shock. And how do the two dogs behave in that new apparatus? It turns out the first dog walks around, gets the warning, gets electrical shock, tries to figure out what happens. Finally, they figure out they can jump over the partition. And from that point on, they walk, they get the warning, they jump, they walk, they get the warning, they jump. They avoid the shock 100% of the time. What happens to the second dog? The second dog basically lays on the ground whimpering. The second dog basically realized that the world is unpredictable, that bad things are happening without control, and the dog gave up on trying to do anything. And that's called learned helplessness. And when we think about fear or we think about stress, there are basically two types. One is, think about like really being busy at work. You have a lot of things to do, you're stressed, you might not finish some things, but it's all under your control. That's a very different kind of stress from a world in which you have no control over what you're doing, which is what learned helplessness is all about. And COVID-19 is basically a period when we have lost a lot of our ability to control the world, right? We don't know, will they let us out of the house or not? Like, just imagine a year ago, I asked you, what are your personal freedoms? You would have made a list that it's unbelievable of the things we've lost. We've lost our ability to plan. We've lost our ability to leave the house when we want to. We've lost lots of things at the same time. Now, if you think about all that and you say that one of the challenges is losing control, the question is, how can we gain some control? Now, can we gain back all of it? Probably not, but can we gain some of it? Absolutely yes. So one way to gain control, I'm not recommending, but one way to get control is what is called shopping therapy. Like, think about shopping, right? You get whatever you want, but you also change the world. You go to a store, you give them a credit card, there's an item that wasn't yours that now is yours. It's an amazing ability to have control over the world. Now, I don't recommend this, but it's one approach. The second approach is to try and exercise small acts of control. For example, I work a lot with low-income individuals on financial and health-related things, and we're trying to get people to actively move money into savings once a week. It's the act that shows I have some control, I'm building something. Physical activity. You want to do physical activity that shows you improvement. So, for example, walking is very healthy, but if you do a plank, with plank you can see improvement. Every few days you can see that you're getting better, or push-ups or something like that. So things that you get some control. Also plans. Make plans, right? Now, will the plan work out? Hard to tell, depending on how long they are, but at least working on the plan and saying, okay, here's a vacation I really want to take. It might not be this year, it might be next year, but all of those activities. So, you know what I love about social science is social science is trying to create an abstraction of what it is that we're doing. And in this case, one of the things that we need to understand is the role of stress in influencing our lives, and then to figure out what we could do to mediate it to some degree. So everything you could do to gain some control is going to be in the right direction.
That's fascinating, Dan. So you're saying that in order to mitigate fear, we can try and regain control on some aspects of our life. and that uncertainty compromises our ability to learn. Can we learn how to deal with uncertainty, how to feel comfortable even though we don't have any control of our lives, or at least our control is much less?
Yeah, so first of all, we do need to try and compensate with some control. The other thing about uncertainty is that a lot of times we learn from experience and we don't learn from description, right? So imagine that you're locked in your house and you have this fear of what will happen if you go out. That will prevent you from going out. But it turns out that if you go out and everything is okay, and a few days later you didn't get sick, you will basically learn that it's not as bad as you thought. I mean, the reality is that it's a terrible illness, it has a lot of effects, but too many people are too afraid. Like if you think about the level of rational fear and the level of real fear, for some people, the real fear is much higher than the rational fear. And sadly, telling them, that the probability of catching corona is, 0.5% or whatever it is not going to be helpful. What these people need to do is to basically become safe, mask, hand washing, social distancing, and so on. But they need to start practicing. So, for example, I also am here at Duke. And for my lab members, we're about 50. One of the things I asked them to do is I said, look, we are basically in remote working, but I want to encourage you to meet some people on a daily basis. It doesn't have to be long, it doesn't have to be anything, but the experience is going to fix it. So, do people need to be afraid? Yes. Do we want the fear not to be too much? Absolutely, yes. And every day that people are at home, isolated by themselves, not doing anything, is preventing the disease but not contributing to their mental health. We need to figure out how to live with this disease, including meeting some people. So we need to create experiences that would mediate our own fear. So for example, I'm not saying take risks, unneeded risk, but saying, you've been at home for a long time, go outside to the park, sit 3 meters away from somebody else, have a discussion. After you do it once, you'll say, nothing happens. Maybe it's not as safe. And in your mind, the fear will go down, 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 down until it would reach some more reasonable level. So we need to work on that, because the people who are having by the way, some people are not afraid enough. But the people who are very afraid, it can have a very negative effect, because every day you stay at home is actually increasing that fear maybe to too high of a level.
So maybe one of the only very few good outcomes of this COVID outbreak is that it'll train us how to deal with uncertain situations, so that if something like this happens again, we're better prepared mentally.
You know what I'm really hoping that this will do, and actually there were 3 things I was hoping it would do, and one of them we've failed. But the first thing I hoped was that it will help us realize how connected we are and how fragile we are. Right? So the world is acting as if we have very different countries that are odd with each other. We have things like global warming that we need to work on together. COVID has shown us in a very, very clear way how connected we are, right? And that's really important. Like, there's lots of challenges. COVID is not the only one that we need to work on together, but that's a very, very salient one that it's hard to ignore. The second thing I was hoping it would show us, and it has, but we haven't taken a lot of action, is how fragile we are. Like, we're creating systems that are trying to be more and more efficient, right? Like, we have hospitals and they're trying to be in 100% capacity, and everything is trying to be very, very efficient. But in an efficient system, when one thing breaks, a lot of things break, and we need to think about resilience in all kinds of ways. And I'm still hopeful for that. The one thing I was hopeful that we will do and we didn't do enough is communicate science. So in many ways, COVID-19 is a highlight for science, right? I, as a social scientist, all of a sudden, right, everybody wants to talk to me. People realize that giving instruction is not as easy, distance education is not easy, domestic violence is going up. People all of a sudden realizing how important it is to truly understand human nature. And if we don't understand human nature, we're just going to have wrong instructions. How do you put money into the economy? The US have put a lot of useless money into the economy. Israel has done some as well. If you put the dollar in, there are smart ways to put the dollar in the economy that would help it move forward, and there are stupid ways to put money into the economy. And of course, biology and the amazing scientists who are working on models for diffusion and medications and vaccinations, amazing work. Sadly, I don't think that the science communication has been that good. So, you know, the people in the science world have been sometimes a bit too excited and say, oh, we have a medication, it's coming out. But if it's not, it didn't give scientists kind of a good impression. So it's a very tough task. There's a lot to do. We really didn't get together. And I think at the end of this crisis, the reputation of science, even though science is doing amazing things, is not going to be better. And that's kind of a really missed opportunity in my mind. We should have thought about that and worked together to promote science during this time.
So you think it's our duty as scientists, and I fully agree, to emphasize outreach in times like this, and to communicate science to the public and explain what COVID is and how viruses work, and how people should behave the way you explained. I fully agree. It's a very important task.
Yeah. At the end of the day, we have to remember that trust is a crucial element for this whole system, right? At some point, there'll be a vaccination, and we would want people to take it. Right now, we want people that wake up with fever and coughing not to leave the house. You know, if you study physics and the elements don't have their own mind, your life is a little easier. When you study things that interact with people, even in biology, you want to create a vaccination, but people have their own will, less than they think, but they have some will. Now you have to create a system where if you want people to do something, they follow up. And you know, the question of when is our responsibility ends? You can say, like, maybe the people who invented insulin, their responsibility ended when there was the molecule. No, if people don't take it and don't take it right, the responsibility has not ended. And I think as scientists, we are at the service of society, right? Our goal at the end of the day to learn, to study curiosity, but at the end of the day, we want to do things that in principle advance society. And if we're not doing the work in a way that would promote usage, then I don't think we're doing our job.
Clearly, the motto of the Weizmann Institute is science for the benefit of humanity, and I think that's a very important message to take home. Dan, you mentioned before that one of the messages you're hoping people will learn from this episode is how connected we are. Do you see a connected psychological response to COVID? Do you see a psychological response which is a response of multiple individuals, which is not simply the sum of many individuals behaving the same way?
So we haven't truly taken this lesson to heart. I mean, even if you look at the European Union, countries are not collaborating. They're actually separating from each other. And groups are breaking away. We see towns working separately because of that level. So far, I don't see the movement I was hoping for. It's not the end of the crisis, so there's still hope, especially when vaccination would come and we'll have to start thinking about how to allocate them and so on. But so far, I'm not seeing there's the realization that we're connected, but there's no enough action on what to do with that.
You know, what I saw in that regard, and that's a response we saw very clear across our campus as well as among our friends, people were looking for ways to make a difference. People were trying to step up to the challenge. Even scientists who had nothing to do with virology or even life sciences looked for ways to turn their knowledge, their talent into making ways that would make a difference. Same is true with philanthropy. You could certainly see people stepping up and trying to use their resource in order to, to do better. Is that a known psychological effect of a crisis?
There was certainly a lot of it. So when the crisis started in the middle of March, I got a lot of calls from the Israeli government, and I showed up in Israel, and I was there for 6 months working day and night on COVID-related things. And the amount of people, scientists and non-scientists, that were basically volunteering their time, and as you said, taking their own tool and exporting and just being at the service of the public good was incredible, right? And I think it had two directions. One is that people realize that they have very valuable tools. So the amount of mathematicians that all of a sudden said, hey, I have something to model and to help with that would be useful tomorrow was incredible. I think it gave a lot of joy, a feeling of meaning to the scientists. And then the other thing, of course, there was the feeling that we are in a time of crisis. And the time of crisis, we're fighting an enemy. And when we are fighting an enemy, in this case, we do get together to try and collaborate. It happens in war when one country is against each other. Like if you said, let's invent an enemy that the world could work toward together, a virus is really good, right? It's attacking all of us in the same way. It shows the similarities between us. So absolutely yes. And what you see happening on the science front across countries is just incredible.
Dan, let me ask you another question. You're a scientist that works on the borderline between behavioral science, psychology, and economy. COVID is not just a virus, it also has enormous economical implications. What is it that we can do in the way we behave in order to meet that economic challenge better? People are losing their jobs, people are using their own savings in order to survive. What tips can you give us?
So where do we start? There's lots of things to say. I'll give you maybe two examples, very different directions. One is we did some research in 2008 about how to give money to the economy in a way that would stimulate the economy. You might remember that both President Bush and President Obama gave a lot of money to Americans after the 2007-2008 crisis. And they did it in slightly different ways. President Bush gave people a refund check. He said, here's a refund of your taxes. President Obama reduced taxes, so people's pay and each pay period was slightly higher. And two different approaches to try and stimulate the economy. And the logic was people would have more money and they would spend more. Turns out none of those approaches worked. President Bush told people, here's a refund check. People said, it's my money. You're just giving it back to me. Why should I spend it? President Obama gave people slightly higher paycheck every 2 weeks or every month. People didn't feel richer and didn't spend any more money. We compared it to something different. We said, what if we gave people a prepaid debit card? Now, you see, if I get a check, it goes into my checking account. In a week, I forget that it came from the government. If I get a prepaid debit card, the money is still on that card. And on top of that, we wrote, spend the government's money. Now you don't think of it as your own money. You think about somebody else's money. It's easier to spend. And on top of that, we asked people to buy American-made. This American money from, we asked people to buy American-made. And almost everybody, almost all the time did that, right? So even if it wasn't obliging them, people were still compliant with that. Now, if you think about this, at the end of the day, you want to stimulate the economy. The US printed, let's say, $5 trillion, Israel, 100 billion shekels. These are very, very large amounts. And the question is, how do we give money in a way that would be effective? So that's one direction, right? To realize that psychologically, a dollar is not a dollar is not a dollar. In standard economics, it is. In reality, it is not. And the way we give the money can change dramatically how people use it. So that's That's one direction. We're going to print money. We're going to try to stimulate the economy. Let's do it in the right way. The second thing, and this is something we did with the British government in 2008, we have to realize that there's going to be large unemployment. And we have to figure out how to help people. In the UK, after 2008, people had to basically submit about 100 resumes before they got a positive response. Think about waking up every day, fixing your resume for a particular job, applying for it, waiting to get something, and mostly getting nothing or negative response. And then you have to continue day after day after day after day. It's a little bit like my dating life. You try, nothing good happens. And we need to understand that this is a Sisyphic task. And we need to help figure out how to find motivation. And what do we do in those systems? We basically change the focus of defining success, not as finding a job, but having your resume in slightly better quality. If somebody responds, even if they say no, you have to feel better about it than if you get no response. We have to understand that this new world of lots of unemployment is going to be very, very tough from the motivational perspective. And we need to basically help people increase their motivation about how to keep on trying. Because if you try for 2 months and nothing good happens, how likely are you going to continue versus saying, okay, I'm just staying on unemployment?
You know, what you just described reminds me a lot of scientific research. Scientific research is also something you do day after day. Most of the time you fail. Most of the time you fail. Most of the results that Mother Nature gives us when we query her is no, that's the wrong idea. But we still have to keep on trying and keep on pushing. And I don't know, maybe you can remark on, on looking at it from a community perspective. I'm sure scientists are trained to sustain this maybe that's the way scientists are selected, to be able to withstand that frustration. But for community standpoint, we know that, looking for a cure for COVID, you're going to try, 10,000 attempts. Only one of them would eventually succeed. What's the right strategy of choosing the way science should follow? Many attempts in parallel, focused attempts.
Yeah, so I'll tell you first of all what I do in my research lab. In my research lab, I basically ask people to aim for about 40% success rate, right? So I tell them, look, if we get too many success rates of experiments, we probably did something boring, right? We did things that were easy to do. We didn't push ourselves. We didn't take the right level of risk. By the way, you can have the same framework in other things as well, right? We could say, look, if you are applying for jobs and you get very easy success rate, maybe you didn't try hard enough, right? You didn't aim high enough. So that's the first thing. And the second thing I do is I celebrate trying rather than success. So for example, what do you do when an experiment was done correctly, right? If you do the experiment wrong, then you don't celebrate. But if you didn't do the experiment correctly and you got the result that you didn't expect, we actually try to celebrate those more than when the result came as we suspect them. Why? Because remember, the goal, the thing we want to reward is the effort, not the outcome. Or think about a kid who is going to school. And let's say you have a kid who studied really hard, but got a test on something that was so esoteric that they didn't do well in the test. Do you want to say congratulations to this kid, or you want to say you got a bad grade? In contrast, think about a kid who didn't study hard at all, but somehow got a really easy test on exactly what the 2% material that they knew. You don't want to reward the outcome. You want to reward the process. And that's true for science, and it's true for everything hard in life. Everything that has a stochastic process between the input and the output, you want to reward the input and not the output. It's true for people with diabetes and heart conditions are trying to manage their health. It's true for scientists. It's true for lots of things in society.
Thank you, Dan. This was very interesting and inspiring. I'm looking forward to meeting you here on campus now that you're guest faculty at the Weizmann Institute of Science, and we'll see you soon at the Q&A anyway. Our scientists are indeed doing important work in coronavirus research, as you've heard and seen. Enabling this kind of excellence is our job in management, in partnership with our friends around the world. Some of the nicest examples of such a partnership that drives excellence are the two prizes we are about to present: the André Deloro Prize for Scientific Research and the Helen and Martin Kimmel Award for Innovative Investigation. I would like to invite Professor Alon Chen, President of the Weizmann Institute, to present the prizes.
Our donor assists us in recognizing scientific excellence in a variety of ways, and one of them is the establishment of prestigious prizes that the Weizmann Institute confers on outstanding scientists every year. The first one we will be awarding today is the André Deloro Prize for Scientific Research. The late André Deloro was dedicated to encouraging science in Israel. The name of the foundation he established, the Adelis Foundation, is seen in many places throughout the Weizmann Institute campus, a reflection of the great generosity of the foundation and its head, Rebecca Buchris. We were honored to present an honorary PhD to Rebecca last year for all that she has done for the Institute. This prize is a very special one that was established in the memory of André Deloro by the Adelis Foundation. Its purpose is to honor and encourage our scientists who demonstrate outstanding research and significant breakthroughs in their field. The award is no string-attached investment in the Weizmann Institute scientist who has evidence excellence in order to enable him or her to achieve even greater excellence. I am pleased to award this year's André Deloro Prize to Professor Dan Oron from the Department of Physics of Complex Systems. Professor Oron's research on the nanoscale is paving the way to the creation of new materials. These new materials have unique properties and they will translate into a benefit for a wide range of applications. Dan will present now to all of us briefly about his research. Dan joined the faculty of the Institute in 2007 and was head of his department. He is the co-owner of 10 patents. He is the incumbent of the Harry Weinreb Professorial Chair of Laser Physics and serves as the director of the Crown Photonics Center. Dan.
Thank you, Alon. I would first like to thank the Adelis Foundation. It is a true pleasure to have your work recognized by deserving such an honor. But before diving deeper into the science, I want to say a few words about mentorship, which is one of the main instruments through which breakthrough science is achieved. Part of the work which I will tell you about today was performed in collaboration with my PhD mentor, Professor Yaron Silberberg, who untimely passed away last year. Yaron was very unique in the scientific landscape, and one of the many lessons I learned from him, much due to my own personal experience, was that students flourish when they're given the opportunity to pursue their own scientific ideas. And this is one lesson I have since tried to apply in my own research group. So when, almost 10 years ago, my student Osip Schwartz came up with a thought to harness the power of quantum mechanics to improve biological microscopes, we both recognized that this is risky, but I agreed that it sounded like an excellent doctoral project. It took us the better part of a year to develop a theoretical framework, which was met by significant skepticism from microscopy experts, as it was considered next to impossible to implement. Indeed, the experimental demonstration was very challenging, but sometimes perseverance prevails. I guess it shouldn't come as a huge surprise that Osip, after a successful postdoc in UC Berkeley, will soon join Weizmann as a faculty member. In any case, let's get back to science. Our story begins at the end of the 19th century with two German gentlemen. The first, Ernst Abbe, was a mathematician from Jena, and in 1873
shortly after the laws of electromagnetic radiation were discovered, was the first to realize that with all its strength, the optical microscope is a fundamentally limited instrument. It cannot resolve features which are smaller than the wavelength of light, about 1/2 millionth of a meter. The second, Max Planck, a physicist from Berlin, discovered about 30 years later that light is not simply a wave, but rather is composed of small, indivisible quantum packets of energy, which we now call photons. Needless to say, the fundamental limit of resolution, as derived by Abbe 30 years earlier, could not have taken this strange behavior into account. More than 100 years later, we have, for the first time, made a connection between these two seemingly unrelated concepts, pointing at a clear pathway to surpass the limit posed by Abbe using the quantum properties of light. To get a better grasp of how this is done, let's take a step back and understand what are the implications of the quantumness of light. To understand the difference between the wave and quantum nature of light, let's look at this picture of a shop window on a sunny day. The photographer is looking at the inside of the store, but simultaneously sees the reflection of the street from the window. This is because when light wave hits an obstacle, the window in this case, it is partially transmitted and partially reflected. In the quantum world, things are dramatically different. A photon hitting an obstacle is either transmitted or reflected, but never both, because it's indivisible. If you look at light emitted by a single molecule using the setup shown, containing a half-reflecting mirror, much like the shop window, and two detectors, the output of these two detectors is anti-correlated. When the top detector sees a photon and clicks, we know that the bottom detector sees darkness, and vice versa. To better understand what is required to observe this peculiar behavior, let us look at a real-life analogy of the situation. In a basketball game, there's just one indivisible ball. This means you cannot simultaneously score a basket on both sides of the court. In order to observe this, you need to keep count of the score at a pace which is much faster than the rate at which baskets are scored. If you integrate over, say, 20 seconds, this is probably too slow, since it's possible to score on both sides during that period. This means that your detector has to be much faster than the natural timescale of the process probed. This is easy enough for a basketball game, where the timescale is seconds, but becomes very hard for light microscopy, where photon emission is extremely fast, less than a billionth of a second. Therefore, in order to overcome the resolution limit derived by Abbe using quantum principles, we had to develop a new type of a camera, which is both highly sensitive and very fast. The output of this camera is not the kind of image you're used to, but rather long strings of zeros and ones representing the times when each of the camera pixels detected a photon. Correlations between different pixels in this stream encode information which surpasses the classical resolution limit. However, a simple demo, elegant as it may be, was not really what we were aiming for. In the 6 years that have elapsed since our first demonstration, we've ardently been working on making this a tool which biologists, like our collaborator, Dr. Efrat Shema, can use. Efrat is looking at specific cancer markers in the cell nucleus, which are too dense to be resolved with a regular microscope. Using our quantum imaging tools and advanced analysis tools developed in collaboration with Professor Yonina Eldar, we have been able to convert the regular blurry images of the cell nuclei into detailed high-resolution quantum ones. And this is just the starting point for us. In the coming years, we hope to push this technology further with the aim of making this type of super-resolution microscopy more accessible to researchers around the world. It took us almost 10 years to push the idea of quantum microscopy from a theoretical concept through a basic science demo to an operating bioimaging pilot. I am thrilled to see where we will stand 10 years from now. Thank you.
Thank you, Dan. I have no doubt we will continue to see more and more great discoveries from your lab in the coming years. The Helen and Martin Kimmel Award for Innovative Investigation is another prize for excellence that enables our scientists to pursue their curiosity and ambitions. The Kimmel Award was established by another major supporter of the Institute whose fingerprints are seen throughout campus. Our science has been enriched by the Kimmel generosity in countless ways for many decades. The Kimmel Award highlights the research of an outstanding scientist to pursue an outside-the-box research avenue. It allows scientists to advance high-risk, high-gain projects that traditional funding sources may not consider. The Kimmel Award gives them the opportunity to fly. This year's winner is Professor Yitzhak Pilpel, who is currently head of the Department of Molecular Genetics. He has already made major strides in system biology and genomics and has developed cutting-edge tools to analyze the network within cells and the evolutionary path that they have taken. Professor Pilpel joined the Weizmann Institute faculty in 2003. He is director of the Ariely Institute for System Biology, as well as the director of the Braginsky Center for the Interface Between Science and the Humanities. He is the incumbent of the Ben May Professorial Chair. Professor Pilpel, please.
Thank you. Thank you, Alon. I'm honored. And thank you to the Kimmel family for this fantastic award. I want to tell you today a story about sexual mating, to ask basic questions about how organisms choose their mate for reproduction and how the choice affects the evolution of the species. And in particular, to ask the question, can organisms choose that particular mate that would maximize the fitness of the next generation? So the study of mating has attracted a lot of attention by geneticists and evolutionary biologists for many years. But I think a key experiment that was done several decades ago was particularly interesting. In this experiment, women were asked to rank potential mates, potential males for reproduction, by just smelling their sweaty t-shirts. And the interesting results of these experiments are A, that indeed they were ready to rank different males according just the smell of their t-shirt. Second interesting result is that each woman had a different ranking. There wasn't any one male that was unanimously attractive by all women. And the third interesting result, perhaps the most interesting, at least to me, is that although each woman had a different choice, there was a commonality among them. They each preferred a male that was neither too far genetically from them, nor too close either, somewhere in between. So that's interesting. Why is that choice being made? And how do we assess genetic complementarity between potential mates? That study was a breakthrough, but to be honest, it left many more questions and controversies than actual answers. The sample size was very limited. Only a few people participated in this experiment. In order to really understand how mating works, you might need to do an orgy. In that orgy, you would collect many, many different males and females, ethnically diverse from all over the world. You would put them together, and you would ask each of them, A, to rank according to attractiveness all the others, B, to actually mate with all others, see how successful mating goes between each pair, to actually have many progenies so that you can have real good statistics about their health and intelligence, etc., and then let all of those progeny compete with one another to ask a specific question. Can we choose a partner that would maximize the fitness of our next generation? But if you think about it seriously, such an experiment cannot be done for ethical reasons, for obvious ethical reasons, but also in terms of the magnitude. We cannot assemble such a cohort of individuals. Even if we go to the tiny fruit fly, it wouldn't be good enough. So rather than this type of more conventional orgy, what about a yeast orgy? Let me first introduce yeast. Yeast are tiny creatures. They are as small as bacteria, but despite looking very much like them, genetically, interestingly, they are more similar to us than they are to bacteria. This is probably the reason that studies on yeast have revealed a lot of interesting biology that pertains to human, even pertains to our health. So yeast is a fantastic model organism. You can fit in one flask in the lab, you can fit as many yeast cells as there are people on Earth, and they are very genetically diverse from one another, as far as we are diverse from each other. So why don't we do that orgy, but with yeast? And for that experiment, we have collected yeast from all over the world. The community has collected yeast from everywhere, from vineyard, from from bakeries, from wines, etc., etc., even from our body or from the ocean or from water or from soil. Yeast are everywhere. So in this experiment, we have collected 1,000 different yeast species, strains. And in this orgy, if you will, they are swimming next to each other and they are making their choices. They mate with whoever they like, and they give rise to progeny to the next generation, and then the next generation is allowed to compete with one another, allowing us to ask, did their parents make the optimal choice when mating to give rise to them? But you could ask me, why did that experiment need to wait for the 21st century? After all, just mixing a few bugs in a test tube is easy. And the answer is actually bookkeeping. In order to keep track of all the mating transactions that go in our test tube, what we did was to genetically engineer each of those cells to carry a little genetic barcode, a unique DNA sequence that identifies each of the parents. When two parents mate, the offspring inherits the two pieces of DNA. Then we induce a chemical reaction that happens simultaneously within all the cells that fuses and recombines the two tags that the progeny got from the two mothers, and then we use the power of DNA sequencing not to reveal a new genome, but to actually reveal the tag in each cell. The first half reveals the identity of the mother, the second half reveals the identity of the father. This way we can tell who mated with whom, who was attractive for whom, etc., etc. Not only that, we can uniquely tag each of the offsprings and see how well do they compete with one another. The study is running in the lab, and it begins to reveal fantastic new biology. It turns out, indeed, that parents do exercise judgment in selecting an appropriate genetic distance, in perhaps maximizing the fitness of their offsprings. In the coming years, with the gift that we have received today, we want to actually decipher the molecular mechanisms that allow them to make those choices, and perhaps even reveal how they have shaped the evolution of the species. So I want to thank you, end here, and thank you very much for listening. I know that genetic lectures tend to be difficult to follow, sometimes very technical. I was given the advice to make this one a little bit more sexy. I hope I haven't taken it too literally. And without, I'll end, and let us just acknowledge our friends, the yeast, and raise a toast. This is for yeast, for health, for peace, and for love. L'chaim.
Thank you, Tzachi. That ends our presentation for tonight, and now I would like to hand the reins back to Roee Ozeri, who will lead the live Q&A session with the Weizmann scientist and Dan Ariely. Thank you to all.